For this lesson, let us discuss properties of bounded variation functions. First, a quick recap. What is variation? So variation is a property we apply to functions. We have functions from the closed interval a, b to r, and we consider a partition on the closed interval a, b. We cut up the closed interval a, b into smaller parts, and then we can calculate its variation sum, which is known as SP. The SP consists of taking the points of the partition, applying f to them, and then calculating the distance of f on the various partition points. So you're basically calculating the vertical distance over the points of the partition. And every partition will give you a different variation sum. And the variation v of the function is obtained by taking the sup of all the possible variation sums. And the sup is taken over all possible partitions. And we say that a function is of bounded variation if this v, this variation, is finite. So for this lesson, we are going to talk about some basic properties of these bounded variation functions. So let's assume that f and g are bounded variation functions whose domain is the closed interval a, b. So the first fact, and we will prove this, is that if your function is bounded variation on a closed interval, then it must be a bounded function on that interval. Okay, the second fact is that these bounded variation functions are linear. Okay, so in particular, if you multiply a bounded variation function by a constant, it remains bounded variation. If you add two bounded variation functions, it remains bounded variation. And if you multiply two bounded variation functions, you get a function of bounded variation. And there's also it's also okay to divide a bounded variation function by another, and that remains a bounded variation, but there is this property you have to worry about. You can't let your function in the denominator be too close to zero. I'll prove the first part of the theorem for this lesson. The second part, I might leave it as a homework. It's not too difficult. I think you can do the second part. So let's first talk about our strategy for proving 2.11. Okay, so we're going to prove the contrapositive of the statement, right? So let's first remind ourselves what the contrapositive is. So our statement is an if-then statement. So we're proving number one, the first part. If f is bounded variation, then f is bounded, right? So p implies q. A contrapositive statement is proving not q implies not p. And basic logic shows that p implies q is the same as not q implies not p. So we're going to prove this contrapositive statement instead of the original statement. So in other words, we are going to prove that if f is not bounded, then f will not be of bounded variation, right? So here is the contrapositive statement. If f is unbounded on AB, the closed interval, then it is not of bounded variation. Its variation is infinite. Okay, so remember that variation is defined as a supremum of the variation sums of these SPs, right? Let me go back to what these SPs are. So these SPs are these like sum of distances, right? And remember that each partition gives you a different SP. Now, if you want to show that the variation is infinite, okay, we have to show that the SPs for every partition, you can get a variation sum that is as large as you want. Okay, in other words, for every positive number m, you can find an SP that is bigger than m. Okay, so that means that the set of all possible SPs cannot have an upper bound. All right, and since the supremum is the least upper bound, well, there's no upper bound, so we just say that the supremum is infinite. Okay, so this is something that we learned in our undergraduate analysis class. To show that the supremum is infinite, you have to show that the set you're taking the supremum of has no upper bound. It gets larger and larger and larger. So in other words, for every positive number m, you can find an element of this set. You can find an SP that is bigger than m. Okay, so this is what we have to show. We assume that f is unbounded, and we're going to try to show this. Okay, and when we write a proof, don't forget that the statement that we are trying to prove will guide us as to what we have to do, right? So the statement is for every m bigger than 0, there exists a partition P so that this SP is bigger than m. Right, so first step is we say let m be positive. Okay, another way to phrase it is to just say fix an arbitrary number m. So remember, we cannot choose the m. Okay, m is positive, and that's the only thing we know about it. We are not allowed to choose the m because we are trying to prove for all statement we cannot choose the m. So m is just a positive number, but we don't know what it is. Now, the next step is that we're going to have to find this partition P. So the statement we're trying to prove says there is a partition P. So our goal is to find this partition P so that SP is bigger than M. Right? So this is the main content of the proof. How do we find this partition P? So remember, our assumption for this contrapositive proof is that F is unbounded on AB. Okay, let's just try to remember what does being unbounded mean. So when a function is unbounded, it can be unbounded above, it can go to infinity, or it can be unbounded below, it can go to minus infinity. I don't really want to divide this into two cases. You can, of course, it's perfectly fine to divide into two cases, f is unbounded above or f is unbounded below, but it can be a bit easier to just consider the absolute value, right? So the absolute value doesn't care if f is positive or negative. So if your f is unbounded, it just means that your absolute value of f is not bounded above. The absolute values can go to infinity. Okay, that's, I think, a bit cleaner than having to divide into two cases, f unbounded above and f unbounded below. So what does it mean that the absolute value of f is not bounded above? It means that for any number, any positive number, we can find an xm so that fxm is bigger than that number. Okay, that's the meaning of an unbounded set. Okay, an unbounded set means you can find an element of the set that's bigger than any number you can think of. So we pick the number that we want to think of as m plus fa. Okay, and this is the sort of thing where I think sometimes students will wonder, okay, where does this come from? Where does this come from? So this is something that when you're writing a proof, we can modify it while we're in the middle of the proof. So maybe you start with saying that I want my fxm to be bigger than m. You'll see that that doesn't work, and then you modify it to m plus fa. Okay, so don't worry right now about how we can choose this m plus fa. Maybe those of you who are students in my class, you can ask me about this in class, and I can explain a bit more. But this is just the correct choice. Okay, we want to choose m plus fa, and we know that there is xm, so that the absolute value of fxm is bigger than m plus fa, right? And I think you can see quite clearly later why this m plus fa is chosen. This, okay? So one particular thing we can notice is that xm cannot be equal to a. So remember, xm is chosen in the domain of f, which is the closed interval ab. But we can rule out the possibility that it's equal to a, right? Because if it were a, then the inequality we just wrote down would say fa is bigger than m plus absolute value of fa, which is impossible since m, of course, is a positive number. If you pull back to the previous slide says that m is a positive number. Okay, so we're not allowed to choose xm to be a, right? Okay, so we know that xm is somewhere in the closed interval ab, but it is not equal to a. Right? It may be equal to b, but we don't mind if it is. So let's just define this simple partition. This partition just says it contains a, xm, and b. All right, there is a possibility, like we mentioned, that xm is equal to b, but if xm is b, just consider the partition ab, right? And that's fine. We can choose a partition that's just ab. That's completely allowed. in the definition of partition. So when we take a partition, right, we calculate the variation sum. Let me maybe pull back to right the beginning of our proof, of our slides, and look at what the partition sum looks like, okay? The SP over here. The SP is taken by the distances between fxi and fxi minus 1. We pick two neighboring points of the partition, we apply f to them, and we calculate the distance, okay? So it's a sum of these things. So when we end up calculating our SP for this partition, one of the terms is fxm minus fa, because a and xm are consecutive points in your partition. So the sum is going to be fxm minus fa distance plus fb minus fxm distance, right? For the first case. For the second case, it's just going to be fxm minus fa, right? In any case, the sum is going to be bigger or equal to fxm minus fa. So we can just use a triangle inequality here, right? fxm minus fa distance is bigger or equal to the distance between absolute value of fxm minus absolute value of fa. Okay. Now, since we assumed that fxm is bigger than m plus fa, so this is where that choice of m plus fa comes in, right? This means fxm must, of course, be bigger than fa, right? So we can remove the absolute value on the right-hand side because fxm minus fa absolute value is positive, okay? So we end up with just saying that fxm minus fa absolute value is going to be bigger than m, right? That's because of the assumption fxm is bigger than m plus fa. But when we simplify everything, we get that this SP is going to be bigger than m. And that is exactly the goal of our proof, right? So if you may remember, the statement that we're trying to prove is that for every m bigger than 0, we can find a partition P so that SP is bigger than m. And we have exactly accomplished that, right? And we're done. Yeah, and this means that this set of all SPs is not bounded above. There is no upper bound, right? And there's no least upper bound. So by convention, we say that the variation, which is a sup of a set that has no upper bound, is infinity. And that concludes our proof. And okay, we've proved the contrapositive, but of course, the contrapositive implies the original statement, right? Not Q implies not P. It's the same thing as proving P implies Q. So let's also talk about theorem 2.2 in the book, right? This one I'm not going to prove. The proof is given in the textbook. You can read it yourself. So let's first talk about refinements. Okay, we say that P bar is a refinement of P if it contains all the points in the partition P, but also contains some extra points. So you can think of a refinement. You can generate a refinement from the original partition by adding the points, but usually we would like to add the points one by one. All right, so let's talk about the variation over intervals. This is our theorem 2.2. So given an f, right? We're not going to assume that f is bounded variation here. It's just a standard. It's just a general statement about variation. If you have a subinterval a prime b prime, so your a prime b prime is contained inside the interval ab. So a prime b prime is a small interval contained in the big interval ab. Then, if you keep the function the same, the variation of the function in the smaller interval is less than or equal to the variation of the function on the larger interval. Okay, that's a very useful fact. We'll use it many times in the course of this class. And there's another fact. So if you have a C between your A and B, then you can break up the variation into the two smaller intervals, right? So if you want to calculate the variation of the interval AB, you can calculate the variation of the interval AC and just add it to the variation of the interval CB. Okay? So in other words, variation is additive on intervals that are next to each other. So again, I'm not going to prove it, the proof is given in the textbook. I suggest you read it. It's really not that difficult of a proof.